Thank you very much. IEEE International Conference on Flexible and Printable Sensor and System 2020. And I will be talking about symmetrical orientation of Spiral-Interconnects for high mechanical stability of stretchable electronics. My name is Nadeem Qaiser, and my other co-authors are Asrar, Damdam, Sherjeel, and Mustafa Hussain from Qaiser University. So let me share the screen first. Okay, so as I said, I will be talking about how the orientation of different stretchable interconnects is affecting the performance of overall flexible systems. So currently using thin silicon and metallic based mechanical compliant, stretchable and reconfigurable electronic devices are providing the way to realize state-of-the-art applications ranging from wearable, flexible, soft sensing robotics, up to electronics and biomedical devices. And there are different strategies to get the flexibility in these devices, like using a compliant material, such as flexible polymers, or the other strategies using the geometries that are stretchable itself due to their particular designs. And there are different geometries people use. Let's say just to name it, a few of them are spirals or fracture interconnects. Similarly, people are using serpentine shapes. So here I'm gonna talk about a spiral-based interconnect and how would you achieve our purpose. We do use an island interconnect structure, where island hold all of the electronic components, and the spiral will accommodate the large deformation during stretching or flexing process. But so far, all of the studies are like showing how these spiral-based interconnects behave, but they have not revealed the mechanics of these structures based on the manner the arms of spiral itself links to the islands. So let's go to the figure 1. So as shown in figure 1, you can see there are two islands on the sides, and there is one more island in the middle. So we say them I1, I2, and I3. And we have connected these islands using the spiral shape interconnects. And usually conventionally used geometry, they have this kind of the figure 1A, this kind of geometry that where they don't really take care that how these spirals are being connected to the middle island, that's I2. So I have proposed a symmetrical series design where you on purpose connect these spirals to the middle island in such a way that they provide more mechanical stability. So what we did, we used the numerical calculations to see how the mechanics is involved in this geometry, and later on we fabricated using microfabrication technique that's shown in figure 2, taking the base silicon wafer and then depositing amorphous silicon and hard mask, and after that we patterned by using lithography our structure of symmetrical shape, and following by the Limoni matching and deep RI, we would use the HF method to release our structures. And you can see in figure 2 the details of the fabrication process. Okay, so let's see the figure number 3. In figure number 3, you can see the comparison of our proposed symmetrical series design to the non-symmetrical or conventionally used one. If you talk about figure E and F, so the stress is, if you compare directly, is 1.6 for our case gigapascal, 1.6 gigapascal, and for non-symmetrical or conventionally used design, it's about 1.7 gigapascal. And similarly, the one thing that I would like to highlight is why this stress is lower, and also why the proposed structure is more stable mechanically is due to the naturally inducing forces. Let's compare the figure C, figure 3C, and figure 3D. So when we take conventional design, you can see when you stretch them out, the outer two islands, the middle island is going to be like in a rotation, and that's because of the torque produced by the nature of the arm, the way it linked to the island. But in our case, it is having a vertical motion, so that vertical motion is not that much severe in terms of mechanics. It's not producing the severe distortions as compared to conventional use. So that's the reason we could get the stretchability that we calculated is 165% for our case as compared to 150% case for conventional use. Now, as you know, it's well known that for silicon-based interconnects, they are expected to induce or sustain a flexibility sustain of 1% before crack occurs. So we have compared in figure 4 at the fracture strain for the both of the designs, and you can see also figure C, 4C and 4D. The tilting effect is very clear at figure 4D. Because of this tilting effect, there is like more high stress at the linkage. So in the figure 5, we have also shown that how it behaves and how exactly it matches with our numerical calculations actually when we fabricate it. So figure 5 shows initial state A, B, C to D, and then when we stretch at a different states of stretching like 90%, 165%, and figure 5D shows onset of fracture. So they are exactly matching with the predictions like predictions by our numerical calculations. So and they are proving the mechanically more stable. So as a conclusion, I would say the symmetrical orientation of spiral around the island provide the high stretchability and mechanical stability, such as it has 165% stretchability as compared to 150%. And also the one by the stress for symmetrical case was found to be 0.22 gigapascal as compared to 0.58 gigapascal. That's actually 163% low. And so results have been validated by using fabricated samples of silicon. And for a complex structure, if we could extend this idea of a mirror symmetry, we can like use this idea to get favorable deformations or on-purpose deformations for different complex, stretchable, and flexible systems. So at the end, I would like to thanks again for giving me this chance to present my work. Thank you, IEEE Flex 2020.